is Radim, and I'm here from Toggle. You might know Toggle. It's let's say world's leading time tracking solution. I don't want to do advert history, so you can try it. If you don't do it, maybe you are interested, because software development teams and consultancies love that. So it's an Estonian company, and today I will talk about profiling and memory analysis for a Go application. It's actually not a good idea to have a black background at the end. It's a bit dark. So just a question. So how many people here are actually using Go in daily business? How many people have more than five services running Go? Okay. And how many people here got failing Go services? Okay, good. So yeah, this is actually everything about how to fail and how not to fail using Go, and how to debug it. And we had a fair share of our experiences with failing and recovering. So yes, I've been working for Toggle for over 2 years. It's a fully remote company. So although it's an Estonian company, we have people all around the planet. A couple of people from Czech Republic. And my other experience is I came through Java background, Python, Ruby, all other backgrounds. I'm a developer, not a developer. So various experiences. So this talk is about leagues. The past leagues, present and future. It actually could be a talk you can have about any single language. I still vividly remember times when this was the main topic for a Java world. How to actually fine-tune the garbage collector, how to find something is leaking, how to find something is blocking. So I actually had the very same talk like 10 years ago about doing the same stuff using Java. And there was always one trick I did use. I had a way how you can dump stack trace from Java, and I had a way how to dump a memory from Java just to see what's inside. And effectively those two or three tricks I had helped me to survive as a Java consultant like forever. Because on every single place I've arrived, it was yes, did you try this? No, you tried, okay, this is a bug, and somebody goes and fix it. Same on memory, and you can just repeat it. In most cases, and it's surprising, most of the software development teams have those issues. And to be honest, we had them as well. That's how I learned how to do this using Go. Go has certain advantages because you don't have to do that much fine tuning as you, for example, do with the Java. I don't want to say Java is bad. JVM is still top of the class virtualization machine that you can have, but Go is different. So you have to actually learn how to do it. The reason why you want to learn how to look inside Go is when you have an issue with one production instance of Go, or any sort of application server, it's actually quite easy. You can observe it, you can see. It's actually a nightmare when it becomes distributed. So if you start talking dozens of different instances, you will suddenly have a very different situation, because most likely that issue won't happen on all instances at the same time. You might employ things like log management. I'm a big proponent of that. But you have to collect data, and you have to collect a lot of data, because unless something is failing constantly 24/7, you probably did something miserably wrong. But most often you will fail slowly, sneakily. 2 a.m. in the morning, you will have a phone ringing that your utilization on one machine is 100%. By the time you go to the line, somebody restarted it, and no information available. So you will start from scratch, and you will spend many couple of nights just debugging such issues. The amazing thing about Go is, main reason why I like Go, one of the reasons, is it comes with a perfect standard library. And actually, perfect thing, it's also this instrumentation is included in the Go standard library. So you don't have to buy any sort of tools that you would do, for example, in Java. Java has it included as well. But you would usually buy some sort of profilers, connect to your instances, and something like this one. Go comes with everything you need out of the box, and that's the beauty of the solution. It's called, the package is called bprof, and it's included on the runtime stuff, and you can use it. Effectively, it's a library that plugs in into the Go runtime, and it can read and write binaries of the data, what's going on with your application. Effectively, at the end of the day, it's just a binary format that you can dump. And that's if you recall the previous slide, it's about collecting data. You can run hundreds of Go instances and just continuously dump data, maybe for a week. So you can at any point go to any sort of memory or CPU data dump and actually analyze what's going on. But because we don't read binary, it actually comes with a very helpful HTTP interface. So for us humans, you can very easily actually get a browser fired up to an instance you have, and you can just read the data using HTTP. It's not going to help you if you have hundreds and hundreds Go routines and millions of objects in memory. But if you have a fundamental issue, it will effectively save your day, because you can just connect, discover the issue, you will see the blocking function, you will see some sort of pattern there. It's actually very easy to do, and all you have to do is do one import. You might start a handler or something, but effectively it's just a one import, nothing else that you need. So what are the use cases where you need profiling? Something might be eating your CPU cycles. Obviously, if your CPU is 100% all the time, that's easy. But if something is slowly adding up, one day it's 10%, another 11, 12, 13. If it slowly starts creeping in, you might have issue. Same with memory. You start a binary which has 3, 4, 5 megabytes in memory, but over time it starts increasing. It's nice to have a monitoring tool that picks it up, that over the last 14 days you ate 16 gigabytes of memory. But how are you going to start digging what's actually allocating the memory? Same one is Go comes with a very easy way how to spawn a safe dream threads, Go routines. How do you find if some of them are leaking? Again, you would have to implement, to be honest, I don't know how to do it without the vprof anymore, because you would probably have to have some sort of a custom system how to track every single time you start something. You would have to have some sort of map, implement it, and then just recode every single allocation you did, every single execution. Or you can recode pretty much any custom resource. And I will try to show you both how it looks like live. How all those different things work for Go. So effectively, once you start your vprof, by default it binds to port 6060, but it's totally your choice how you want to run it. All you want to do is connect to this URL. I will try to see if I... Okay, I don't know. So effectively, how it works. So effectively, this is the very simple way how you can connect to the debugging of a live instance. So this is actually one of our production servers, one of the small instances we have. So you can see there's a couple of the profiles. Those are predefined. Profile is actually what is being tracked. So as you see, this binary at this moment has no blockings, so there's nothing waiting to get access, no network level blocks. Go is nice that actually it's full asynchronous, so blocks are very effective. You can see that right now there's 30 Go routines. This is the sort of human-friendly display, so you can see there are 4 Go routines waiting for some, I would say it's the HTTP reader, another 4 just doing some sort of write loop. Yeah, there's another connection waiting. So yeah, right now this instance is not doing anything. You have some sort of keep alive on a database connection. Yeah, everything is in always. And we on this particle scene we have not actually. I'm trying to refresh it. Maybe we will be lucky. And we are not. But let's see, in the later stages, we will actually capture like maybe a minute of the traffic, so you'll see a flow through the source code, so you'll see actually where the time and memory allocation went, and that's why actually it's becoming helpful. So the third profile is a heap. So here you can see all the objects in memory, how they are in your Go application allocated. So you can see most of it's some sort of gzip, bugsnag notification, handler, regular expressions in our code, a lot of regular expressions. They will mainly come from the routing, because we're using routing, I think it's Gorilla, and it just allocates it. If you want to try to optimize your Go application to extreme limits, you can play with this quite a lot, just to see what your Go application is really allocating. For us, it doesn't matter. The binary takes a couple megabytes in memory. That's the beauty of the Go, that our main API that powers the backend is just megabytes. Just the Go. It's actually very simple. And if I just scroll down, yeah, you see we have some metrics. I will actually talk about that later. Yeah, just stuff that we have in memory. Connection is not the fastest. Okay. Same. You can have your semaphores root axis actually allocated. So if you have some sort of need to do a manual synchronization, you can actually observe them live. So as soon as you will start doing some sort of pretty heavy parallel stuff, you can actually observe it by default. You don't have to do anything. So everything which is using the Go standard library will be created, and then you can have a thread create and the full Go routine dump. So previously we seen the aggregation, and now it's just every single Go routine which is running is just dumped there. So this is, for example, one of the tricks I was mentioning in Java. So if you have issues, this is a number one point where you need to look. Because if you have a function stuck at 7 point in the code, you have your blueprint, then you need to find what sort of blocking it is. It could be resource-based, network-based, it could be utilization-based, whatever you actually. It depends on your application. But as I said, web is good if you want to manually read it. But if you're going to analyze an actual problem which happens over time, Go actually comes with tools that read those binary data. So you can have you see the URL is still the same as I used on the web, but actually it will download that binary to your local machine, and it will do the analysis on the machine. So same one, you can do the CPU tracing, and you can do the memory tracing. So if I just show you, so as you see, right now it will spend 30 seconds capturing all the CPU data from that instance. So what we've seen before was just a one-time snapshot. It didn't say anything. But right now it will actually collect, and you can configure it for as long as you want to collect the data. So right now, half minute should be over any time, and it will download the binary. You can save it for later. So that's again, very very helpful if you have a distributed environment with hundreds and hundreds machines. So you can see you found it. You can find it stored in your current folder. So you can use it. You can just use any sort of file management system. And the beauty is, for example, top 10. So right now, those were top 10 most CPU intensive operations performed in that time frame. So you can see pretty much, the one important one is, bcrypt is going on. So right now I can say that the most CPU power goes to people logging in, because we're using bcrypt. So that's the most CPU intensive operation in that instance, and then pretty much memory allocation that's going on. Nothing that would go out of ordinary. As I said, we are humans, so this is actually not helpful, but this is actually where the fun starts. Right now, you see complete map of what's going on in that instance, so you can actually start zooming in. And if we find the entry point, you see this is our method that obviously starts the API web interface. You can see then most of our function requires user authentication. So you see that 5.21 seconds were spent doing something with the user authentication because every single request has to go through it. Then you see there's obviously garbage collector, also Redis connection, loading users up, down to a database level, and then you can actually trace it all the way to every single statement that was happening at that time. So you can see without doing anything, you don't have to enable any flag on the Go application, and you can effectively get anytime information what your application is doing. And this is actually an amazing thing because, for example, last time we had an issue, all it took, it was a kind of difficult issue based on the resource usage, but it took about 15 screenshots like this one, just to characterize visually what are the differences, just to find the critical part, how to find a function that was causing issues. Again, it wasn't an issue that application would crash or application would go bonkers within seconds. It was a slowly creeping issue that we just ate 100 kilobytes every minute. And we had this warning when the memory ran out, process was restarted, but we had an issue how we're going to get back. So this is actually a way how you can do it. You can orchestrate this one, you can have it automatically saving those dumps. And if you're going to do some sort of diagnostic of the issue, this is what will save your technically your production, I want to say ours. So this was the CPU profiling. You can do the same one with memory. There you don't have to wait, obviously, because it just analyzes what's currently in the heap. Okay. Again, you have the same top 5, whatever. Easiest one is the SVG. So yeah, and here you have, so you have again from the HTTP server all the objects. So for example, for us, you can see we have a quite heavyweight list of cross-origin whitelist, which is just a simple list of strings. So there's just no way how we would save memory there. But if you scroll down, you can see how much memory for example Gorilla routing takes. In our instance, you can go all the way up to matching of the strings, and by the size only, you can see this is one of the biggest consumer of memory for the instance which is running for a day's week. I'm not sure when we did the last deploy. It's probably days or hours. On all fronts, you can probably see if you're using Go, you will see a lot of familiar components. So effectively, here you see processing of certificates. Again, regular expressions are quite high on that list. You see, database connection handler. So we always keep some sort of connections open. Effectively, as soon as you start having any sort of memory-related issues, those boxes will explode. They will be huge. All the boxes will be small, and if you have such an issue, you will simply see it. There's no other tool to make it so easy. With other solutions, Ruby, you have to buy stuff that actually does it. As I said, Google Go is actually so trained because it comes out of the box with all the tooling you need. So it's not just a library that covers functionality. It's also the diagnostic.
May I have a question? There is an arrow going back to the main. What does it mean? That big.
It's a Bugsnag. It's the error tracking tool we use, and it's using own HTTP 7.
Okay.
So it's kind of a loop because I wouldn't say it's a particularly 100% best implementation, because what they effectively do, they will relaunch the application when you start it. So they will wrap everything what we do in own stuff, which is to capture all the errors. So I'm going to find what I was going to talk about. So yeah, seeing is believing. So this is actually the stuff that you need, because it's a command line base. You can just save those screenshots all the time. So it actually, you don't have to wonder what happened at 2 a.m. You just can collect the data, the binaries, and you can just analyze that. I know I already said the word cool so many times, but this is not only for a resources that comes out of the box. You can use the bpro for anything. So for example, what you can do is you can create own profiles. So for example here, I'm just creating a demo profile. So let's say we have a resource which is limited. It could be a database connection, I will mention it later. And you create a profile by certain name. The convention is you should use the same name as a package name slash name of that resource or that profile. The reason is simple. You never know what have you rendered in. So in case you rendered something that has a demo profile that somebody forgot in, it will just panic your application. So it's always good practice to name it. Here you see, I'm just exposing it under a different URL, so that it's available on the web. And all it does, every single time it arrives to a block which does something that you want to measure, you just add and then remove. That way you can track how much allocations you have of certain object, and easily spot things like when where the code is leaking. The difference between 0 and 1 is whether you want this call to be included in the stack trace or not. So I'm not sure if you can see it. There's actually the code is live on the Golang playground. I will make the slides available so you can just take it, paste it on your machine, and just try it. It won't work on the playground because it's limited in instrumentation, but you can use it. So just to wrap up, and we still have some things to cover. Where do you use the profiling and memory analysis? Obviously, leak detection. If you have issue, this is the primary tool which you will use to find what's going on. But as I mentioned previously, it's about the precious resource acquisition. One of the most precious, at least for us, I believe for all of us, is going to be a database connection. Database connection, no matter how read-only replicas we might have, at the same time, database connection is still an issue. So what you can do using the code on previous side, you can wrap all the connection retrieval by this new profile add remove, so you can actually see live, because Go does not allow easily to kind of debug what's inside the connection pool. So you can wrap it and start monitoring what actually takes your connection, how long you spend, and generally fine tune. For example, we have a stuff built around this one, so I will continue on that topic. Also, the one thing that we yet to implement, but it's kind of goal we want to have in the future, is when you're running a high demand service, usually when something happens, things start accumulate. So if you suddenly have, I don't know, 200 open connections and something blocks, you have no time to wait. So because within the minutes you will have hundreds, maybe thousands connections queued up, and they will make the problem much worse. So the common way how to solve it is the circuit breaker pattern. Effectively, it means once you start hitting some sort of critical threshold, you will break it. So that means if you hit a connection pool limit, the soft one, you can start refusing all the connection from outside. So effectively everything will break up to the client. So in a normal scenario, it would be that you know that you're receiving HTTP 500, but the new connection would be still hitting the database, still would be queuing up to the certain time, and they would be still, taking that very needed space for you to diagnose the issue, to actually work on it, and it makes the recovery. Because, for example, when you have a queuing system in your architecture, what will happen after such a thing? You will hit the problem, you will go down. If you can recover in 5 minutes, then you will start processing those million messages, events that happen when you are down. And then you have actually extended downtime because what will happen? It will take all the resources to process through that queue. So using the bprof custom detection is actually a perfect example. What we actually do, and this is a live system chart. We use all this to track the connection to database. Internally, we don't do anything if the connection is returned within 100 milliseconds. If the connection is returned after 100 milliseconds, we start putting it into log files so we can easily spot the problems, so we can correlate the actions. And this whole circuit breaker will start refusing if there are delays more than 15 seconds. So if we know that 15 seconds, something takes more than 15 seconds, we will just start killing all the incoming requests to retrieve the database connection, because we might have a network issue, we might have a database issue, we might have whatever. What we don't want is to queue up the users, let them suffer, because it's easier on the user experience to say, oops, we have an error, instead of some spinning wheels going on online for all the users. Maybe it's one instance. If it's one instance, then load balancing will take care of it. If it's across the board, they will just fail. It's easier because they will just see, oh, there's a problem, and it's fine. We will still have the minority of the users facing that issue, but it's not 100% of the user base. So actually people know that something is wrong, we can display much more helpful messages and work with it. This obviously needs a bit more work. So we have a ticket-based allocation of database connections. So we have a custom wrapper around all the database connections. It's implemented on a tickets based. So far, it's still not connected to the bprof stuff. It's an in-house build. We have 2 queues for write and read-only connection because we're using Postgres. So single master situation for main service. Obviously, write connections are really precious because we don't want to exceed those. And read-only are fine relatively because we have many replicas that can be hit, but still we don't want to have that scenario where everybody just waits for a connection. So those charts I showed you, that's the meaning, but effectively we're using a Go metrics library, which helps you to time stuff. So we don't actually care about timing of one single metric or the database connection time. What we care is last minute 95% percentile. If we know that this is over 100 milliseconds, we know something is wrong. That way we can easily skip if some request takes a second and other 200 within that minute interval are okay. It will still be fine, no other thing will happen. And effectively, if something goes wrong, we hit that, we will just kill everything. So it does. Another application of this this particle pattern of the usage could be in microservice-based architecture. So our architecture actually is many Go services, and again, same can happen with the database. Do we want to stop a user from doing something if one of the services stop responding? No. We want to, again, accumulate a critical mass and make sure we can kill things as soon as something is going on. So that means if we have, for example, We have own in-house onboarding manager that tracks user events on the website and the application. If that part of the architecture would go down, we have no reason why to stop users, because it's absolutely fine to receive 500s internally for, I don't know, minutes, maybe even hours. You will just lose visibility of what users are doing. But it means users will still be able to go use the application without any issues. We wouldn't try to do any more Go routines, because as you would probably now understand, if one service failed and you would start piling up Go routines, you would again acquire hundreds, thousands of Go routines pretty quickly. If this would happen, let's say, on the US working time, it would be able to break it down the application within minutes. With a tooling like this one, we can sustain pretty much, I would say, hour or two without any major issue. Obviously, because we're using the very similar system for a status reporting on all the components, we would get alerted on not the primary high critical level, but we would get on the secondary level alerted that something is going on, and we can start to investigate it, maybe just restart, maybe investigate it if it's some sort of networking issue. Okay, I pretty much covered this slide. One goodie which is still in the vProf is the live tracing. So it's similar to what we've seen, but it just gives you a much more detailed data. So I will try to again connect to the so now I will be capturing actually everything was going on in that. Oops, I was disconnected. Yes. Maybe we will connect. Maybe not. Okay, not sure if the Wi-Fi works. I'm trying to connect using my phone. So just a second, I will try a different connection just to see. Okay, I'm connected. So let's see if we have more luck. Okay, so that works not better. So now I will start again collecting 5 seconds of everything what we can find in that instance. What does it do? So yeah, this is one of the demos when the demo does not go as expected. Okay, so I will show you this one. I will try to figure out what's the issue. But effectively, it will give you a display like this one, just with a different views on your VM. So it will give you a profiling on the CPU level. So what time, when, again with the charts. It will give you a blocking analysis. So for example, you can browse down by the functions using any sort of blocking functionality. So in this case, you would see all the logic that went out, let's say, on networking level, and what initiated it. So that's just a different views how you can look at, how you can review what's going on inside the binary, and effectively that just complements what's available on the bproc. So I believe that is all what my presentation covered. So we are Toggle, just in case you are interested, we are Array. So, any questions?
There is a functionality in for heap dump. Have you ever tried it? Because it was useful until version 1.4, I think, and they removed type information from the dump. And I was not able to find some tool which is able to analyze the dump, because it will be quite useful if you are able to get some statistics on how many instances of some structure, for example, are allocated on the heap.
I believe number of instances is not there. The heap one actually will give you, let's try it if it works. What's actually on the heap? Because I know there was a change. I believe there was 1.4.
Actually, it's quite a different thing. There is functionality for heap dump. This is information about functions and how much memory.
Oh, which function? Okay, no, that's gone. I haven't seen it. Right. In a tooling so far.
Yeah.
Yeah. So yeah, that just confirms what you found.
Yeah, because there is a function to dump, but nothing to read it.
Okay. I can actually look up, just in case, and add it to the slides. But I know it was missing, but so far didn't have a reason to actually look for it, so I did not.
So what's the performance cost for Profiler?
Almost nothing. There is a slight hit when you actually tracing the data. So from our experience, well, let's start on memory. When you keep the bprof running on the web interface, that's almost negligible. You don't see any sort of difference. If you try and trace data, there is something like 20% utilization of CPU up. But you don't do it for extended periods. So you usually do it like a short segments of time, just to get the data, or you do it under circumstances where you actually don't care. So I would say we have all the bprof enabled by default in production, and we haven't seen any long-term jump in CPU usage or memory usage. Because the Go binary comes with that instruments by default. By using it, you are only exposing them. Okay, any more questions? So if you have any more questions about Go, how we're using, or about us as a Toggle, as a remote company, how is it to work remote, just grab a beer and we can have a chat.
Whee!